Here's your notes for section 2.1, the start of the chapter. We are going to be describing patterns and using inductive reasoning. I have a feeling this is stuff that you've seen before and that is relatively easy to catch on to, especially some of you who like to find patterns, some more than others. A couple vocabulary words, not nearly as bad as the introduction to the other chapters in vocabulary. Just a few. Conjecture is one of the vocabulary words, and again, if you have this on a handout, please read along, but make sure that you understand what it is it's saying. A conjecture is an unproven statement based on an observation. Sometimes you could make a conjecture in science as well, like, I wonder what, it's kind of the same as a hypothesis. It's the statement that you're making because you've seen some observation. We are going to do inductive reasoning from there, which is used when you find a pattern in specific cases, and then you write a conjecture for the general case. You find a pattern in a specific case, and then you're going to write a conjecture for the general case, basically saying it works all the time. Here's an observation in a specific pattern, but the conjecture says this is going to work pretty much all the time. So conjectures and deductive reasoning. Describe the pattern in the numbers. So if you take a look at those numbers, you have -7, -21, -63, -189. You can try adding, subtracting, multiplying, dividing, fracturing, squaring, anything that is necessary. This one we started out relatively simple, and it recognizes that 7 times 3 is -21, -7 times 3. -21 times 3 is -63, times 3. So then it says write the next 3 numbers in the pattern. Go ahead and grab your calculators. Please don't do these in your head and get them wrong because you're doing them too fast. -189 times 3 is -567. Oh, I like that number, 567. And then take that one times -3, or times 3, and you get 1701. And then you take that number times 3, and you get -5103. Sorry, all 3 of them are negative because we're just multiplying by positive number 3. And then you could put ... saying this is going to continue, but we only found those 3 in the pattern. Okay, next one. Numbers such as 3, 4, and 5 are called consecutive integers. If you haven't heard that before, consecutive integers means any 3 numbers in a row. If they said consecutive odd integers, you would say 3, 5, 7. If they said consecutive even, you would go 2, 4, 6. But when it's consecutive integers, it's just 3, 4, 5. We have to make a conjecture and test a conjecture about the sum of any 3 consecutive integers. If we took any 3 consecutive integers and added them up, could we make a conjecture about it? Well, let's try a few first. We'll start with 3, 4, 5, since that's what they gave us. And we'll take 3 plus 4 plus 5, which equals 16. No, it doesn't. That's not good. 3 plus 4 plus 5 is 12. Let's try 8, 9, 10. 8 plus 9 plus 10 is 27. Let's try, bigger numbers. 100, 200, 100, 101, 102. And we get those. We add them all up. We end up with 303. We could try negatives. We have to be integers, so they have to be whole numbers. What if we did -5, -4, -3? That adds up to -12. Make and test a conjecture about the sum of any 3 consecutive integers. I don't know if you can see or recognize any kind of pattern, but this is the kind of things we're looking for today. As you look at it, take a look at the middle number. There's 3 numbers, 3, 4, and 5. If I gave one of these numbers, took it off of the 5, and put it over on the 3, we would have 4 plus 4 plus 4, which is 12. If you want to take the big number, just borrow one of those numbers, put it over on the smaller number. We'd have 9 plus 9 plus 9. 101 plus 101 plus 101. We'd have -4 plus -4 plus -4. Or in other words, you could take the middle number and multiply it by 3. Multiply the middle number by 3. Got to have 3 consecutive integers for this to work. Multiply the middle number by 3. And it works every time. 4 times 3, 9 times 3, 101 times 3, negative 4 times 3. Could you do negative 1, 0, and 1? Multiply the middle number by 3, and you would get 0. Negative 1 plus 0 plus 1 is absolutely 0. Works with negatives, works with positives, works with 0, but we are only working with integers. So that's the kind of stuff that you're going to have to come up with on your own on some of these. Another vocabulary word. What about a counterexample? We talked about counterexamples when we did biconditional statements. Same idea. A specific case for which a conjecture is false. So we have a conjecture, and we're like, we're going to state this, but then one case, one specific case, makes the whole thing wrong. Okay, if I said everybody in my class is 15 years old, and there's one person in here who's plenty advanced and they're 14 years old, that is not a true conjecture. I can't say everybody in the class is 15 years old. If there's one student who's 14, it makes the whole entire conjecture false. So let's try it with this one. Here's a conjecture. The sum of two numbers is always greater than the larger number. Seems like a pretty reasonable conjecture. Totally makes sense. If you're going to add two numbers, I don't know, 7 plus 15, you're going to get a bigger number. Because if you take two numbers and add them together, you're going to get a larger number. So some would say, yeah, that conjecture is true. But you got to be careful. There are some instances. Some people hear the word number and they just automatically go on the positive side of the number line. Is it true or false? It's false. Find a counterexample. What if I took 7 plus negative 15? I did sum, so instead of doing 7 minus 15, if I took the number 7 and I added negative 15, I would get negative 8. Is that greater than the larger number? Negative 8 is not bigger than 7. No, it is not. You could use any negative number would be a counterexample. You could use 0. 7 plus 0 is 7. If you add any two numbers, it's always greater than the larger number. It's not greater than in this case, it's equal to. So a counterexample, you could either give a specific one example, or you could say one number is negative. Or you could also say one number is 0. Either one of those would be a counterexample, or a specific case where you just show something mathematically would also count as a counter example. Next up, along with conjectures, we're going to write a function rule. So we're going to tie this back into algebra. We do that quite often. Relating x and y. Here's your x and y. We have to try to figure out what happened to 0 and 1 and 2 and 3 that turned it into 0, 1, 4, and 9. Now those seem like kind of a strange pattern because the 0 stayed 0, the 1 stayed 1, but the 2 didn't stay a 2 and the 3 didn't stay a 3. We could try adding and saying 0 plus 1, and here we added 3, and here we added 5. I don't know if that works so much. But if you take a look at this number, if you square a 0, you get a 0. If you square a 1, you get a 1. If you square a 2, you get a 4. If you square a 3, you get a 9. So that's a pattern. That's why we're doing this in this part. This is a repeating pattern. How do we write it as a function? We say that all the y's are equal to the x squared. And when we write functions, I don't know if you remember this from last year, functions are always written as y. Is this a true statement? Yeah, it's true, but not technically written as a function because functions say what happens to the x that made it become a y. So we're not allowed to write it the other way. All right, very short notes today. The last one we're going to talk about is the Fibonacci numbers. Some of you have heard of Fibonacci numbers. Some of you have some of them memorized. Maybe you want to memorize 10 of them, 20 of them. Starting at 1, although some might argue that Fibonacci start at 0. I was taught way back in the day they started at 1. I think they added the 0 later. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. Trying to find a pattern. Okay. Oh, I forgot a comma in there. We add 1, add 1, add 1. Now we're adding 2. Now we're adding 3. Now we're adding 5. Now we're adding 8. Now we're adding 13. Okay, so there's no pattern in what you're actually adding. But after the first 2 numbers, after the 1 and 1, each number is the blank of the previous numbers. The blank of the blank previous numbers. After the first 2 numbers, so we got this 1 and 1, each number, this 2, came from 1 plus 1. This 3 came from 1 plus 2. This 5 came from 2 plus 3. This 8 came from 3 plus 5. How are we going to fill in the blank? Each number is the sum of the 2 previous numbers. If I look at this number 89, it's 34 plus 55. If I look at the number 21, it's 8 plus 13. Write the next 3 numbers in the pattern. If we're going to go with the next 3 numbers, dot, 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 it came from 89. And I probably should have a dot, dot, dot up there as well. 89 plus 55, and yes, I'm using a calculator so I don't make any mistakes, is 144. And then take 144 plus 89, and you get 233. Then take 144 plus 233. Keep adding the previous numbers, 377. There's a nice little pattern in itself. Double 4s, double 3s, double 7s. Let's see if it keeps up just for fun. If I add that to 233, nope. We get 610, which breaks the double-digit pattern. But it's still part of the Fibonacci. All right, that's all I have for notes, but I am going to put up for you this Fibonacci video because it's amazing. Not only because Vi-Heart talks so fast that you can hardly keep up with her, but you maybe have never seen the Fibonacci series in nature. Oh my goodness, I spelled it wrong. This is like my 3rd mistake. Fibonacci series.
Say you're in math class and your teacher's talking about, well, who knows what your teacher's talking about. Probably a good time to start doodling, and you're feeling spirally today, so yeah. Oh, and because of overcrowding in your school, your math class is taking place in greenhouse number 3, plants. Anyway, you've decided there's 3 basic types of spirals. There's the kind where as you spiral out you keep the same distance, or you could start big but make it tighter and tighter as you go around, in which case the spiral ends. Or you could start tight but make the spiral bigger as you go out. The first kind is good if you really want to fill up a page with lines, or if you want to draw curled up snakes. You can start with a wonky shape to spiral around, but you've noticed that as you spiral out it gets rounder and rounder. Probably something to do with how the ratio between 2 different numbers approaches one as you repeatedly add the same number to both, but you can bring the wonk back by exaggerating the bumps and it gets all optical illusion-y. Anyway, you're not sure what the second kind of spiral is good for, but I guess it's a good way to draw snuggled up slug cats, which are a species you've invented just to keep this kind of spiral from feeling useless. This third spiral, however, is good for all sorts of things. You could draw a snail or a nautilus shell, an elephant with a curled up trunk, the horns of a sheep, a fern frond, a cochlea, and an inner ear diagram, an ear itself. Those other spirals can't help but be jealous of this clearly superior kind of spiral. Better draw more slug cats. Here's one way to draw a really perfect spiral. Start with one square and draw another next to it that is the same height. Make the next square fit next to both together, that is, each side is length 2. The next square has length 3. The entire outside shape will always be a rectangle. Keep spiraling around, adding bigger and bigger squares. This one has side length 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and now 21. Once you do that, you can add a curve going through each square, arcing from one corner to the opposite corner. Resist the urge to zip quickly across the diagonal if you want a nice smooth spiral. Have you ever looked at the spirally pattern on a pine cone and thought, hey, sure are spirals on this pine cone? I don't know why there's pine cones in your greenhouse. Maybe the greenhouse is in a forest. Anyway, there's spirals, and there's not just one either. There's 1, 2, 3, 4, 5, 6, 7, 8 going this way, or you could look at the spirals going the other way, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Look familiar? 8 and 13 are both numbers in the Fibonacci series. That's the one where you start by adding 1 and 1 to get 2, then 1 and 2 to get 3, 2 and 3 to get 5, 3 plus 5 is 8, 5 plus 8 is 13, and so on. Some people think that instead of starting with 1 plus 1, you should start with 0 and 1. 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, and it continues on the same way as starting with 1 and 1. Or I guess you could start with 1 plus 0, and that would work too. Or why not go back one more to -1, and so on. Anyway, if you're into the Fibonacci series, you probably have a bunch memorized. I mean, you've got to know 1, 1, 2, 3, 5. Finish off the single digits with 8, and ooh, 13, how spooky. And once you're memorizing double digits, you might as well know 21, 34, 55, 89, so that whenever someone turns a Fibonacci number, you can say, happy Fib birthday. And then, isn't it interesting that 144, 233, 377, but 610 breaks that pattern, so you'd better know that one too. And oh my goodness, 987 is a neat number, and well, you see how these things get out of hand. Anyway, 'tis the season for decorative scented pine cones, and if you're putting glitter glue spirals on your pine cones during math class, you might notice that the number of spirals are 5 and 8, or 3 and 5, or 3 and 5 again, 5 and 8. This one was 8 and 13, and one Fibonacci pine cone is one thing, but all of them? What is up with that? This pine cone has this wumpy, weird part. Maybe that messes it up. Let's count the top. 5 and 8. Now let's check out the bottom. 8 and 13. If you wanted to draw a mathematically realistic pine cone, you might start by drawing 5 spirals one way and 8 going the other. I'm going to mark out starting and ending points for my spirals first as a guide, and then draw the arms, 8 one way and 5 the other. Now I can fill in the little pine coney things. So there's Fibonacci numbers in pine cones, but are there Fibonacci numbers in other things that start with pine? Let's count the spirals on this thing. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The leaves are hard to keep track of, but they're in spirals too, of Fibonacci numbers. What if we looked at these really tight spirals going almost straight up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. A Fibonacci number. Can we find a third spiral on this pine cone? Sure, go down like this, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. But that's only a couple examples. How about this thing I found on the side of the road? I don't know what it is. It probably starts with pine, though. 5 and 8. Let's see how far the conspiracy goes. What else has spirals in it? This artichoke is 5 and 8. So does this artichoke-looking flower thing. And this cactus fruit does too. Here's an orange cauliflower with 5 and 8, and a green one with 5 and 8. I mean, 5 and 8. Up is actually 5 and 8. Maybe plants just like these numbers, though. Doesn't mean it has anything to do with Fibonacci, does it? So let's go for some higher numbers. We're going to need some flowers. I think this is a flower. It's got 13 and 21. These daisies are hard to count, but they have 21 and 34. Now let's bring in the big guns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 17, 20, 24, 42, 53, 54, 55. I promise this is a random flower and I didn't pick it out specially to trick you into thinking there's Fibonacci numbers and things, but you should really count for yourself next time you see something spirally. There's even Fibonacci numbers in how the leaves are arranged on this stalk, or this one, or the Brussels sprouts on this stalk are a beautiful, delicious 3 and 5. Fibonacci is even in the arrangement of the petals on this rose, and sunflowers have shown Fibonacci numbers as high as 144. It seems pretty cosmic and wondrous, but the cool thing about the Fibonacci series and spiral is not that it's this big, complicated, mystical, magical supermath thing beyond the comprehension of our puny human minds that shows up mysteriously everywhere. We'll find that these numbers aren't weird at all. In fact, it would be weird if they weren't there. The cool thing about it is that these incredibly intricate patterns can result from utterly simple beginnings.